Welcome to this teardown video of the Well RSP-2000-48. Look at the specification sheet here. It reveals this is a really powerful beast. See, 12.3 amps of input if you are in the 200 to 240 volts AC input. Wow, this is more than most people got. And the output 48 volts, 42 amps. So yeah, that is 2000 watts of output. Amazing. Also, you will see these really big terminals for the output. Really nice. The size of this is really big. So compared to my hand, it is, yeah, 2 hands, 30 centimeters wide and 13 centimeters wide, and it's 4 centimeters high. Its weight is 1.8 kilos, so it is definitely really heavy. This block diagram isn't really that detailed, and it isn't really that correct either, but it will show the main parts: EMI filter, active inrush current limiting, rectifier and power factor correction, and a main power switching, a transformator, rectifier filter, O-ring FET, so this is a module, the O-ring FET control, and then you have your output. You have over voltage protection and some detection for voltages. You have a microcontroller that is connected via optocouplers to a main PWM control for the main power switching, and you have a PFC control module that is controlling the PFC system. It looks a little bit like you have 2 different CPUs. This is of course not the case. There's only one CPU in this power supply. You also see an auxiliary power supply that is running off the DC after the PFC. So this is correctly drawn, and you have a fan that is also controlled by the MCU. And this auxiliary supply got rectifiers and filters for the different voltages that is used inside this system. Data isolation for external data and external communication to O-ring systems and such. So this is what it contains on their block diagram. Open. So let's have a look at the internals and explain in more details how this one is designed. I did the double check that the wire here is disconnected, so it shouldn't be dangerous. First, the normal common mode input filter. There isn't much to say about this. This is very normal. However, you will see those little diodes, or those little, it looks a little bit like glass diodes when you look, and they are on each side of the common mode chokes. They are in fact gas discharge tubes, GDTs, and they will shorten if there's a very high voltage across the coils. So that is mainly if there is a like lightning or a high voltage surge. Then they will protect the input filter and guide all the lightning surges directly down to the capacitors here, and then it will go into the chassis and earth. That means there's a high risk of anything else will survive a lightning strike. Then you have 2 rectifiers here in parallel. Let's move this so we can see. It's because they this is a normal rectifier, bridge rectifier technology, so that means there will be quite a lot of loss in those. And this is also why it's relevant to put on a lot of heat sinking and a temperature sensor. Well, it's not really a sensor, this is just a device that will give an alarm if the temperature is too high. So that is good. Then after the rectifier, this is really difficult to see, and this is why I have another one that is blown up that I can show you guys, so it's easier to see what is going on. I took the heatsink off the rectifier. This little capacitor here is only 2.2 microfarad. So this is what contains the DC after the rectifier. So this is about 300 volts if we're running in 230 volts area. So now those 300 volts of DC goes through two NTCs in parallel. Those are 20 ohms each, so parallel 10 ohms. And this goes through the switch of a relay. At the first it is of course open, so the voltage goes through 10 ohms. This is in-rush current limiting, and this is very useful for charging the three main capacitors here slowly, so you don't blow the main fuse, and also so you don't break anything here, because the charge current is really big. You got three of these babies in parallel, so there's a lot of stored potential energy here. We are charging this via two different ways, and also I'm going to show you this is the PFC. This is actually a little bit special, this PFC, and this is why it's also interesting to see this. So this is the PFC controller board, and this controller here is called UCC28070. It is an interleaved PFC controller, and this will control these two out of phase. So it looks like push-pull, but of course it's not push-pull. This is just interleaved operation, and this one is running at 110 kilohertz. So you see two of the fets and one diode for one system, and the current sense for one system, and then there's a diode and two fets for the other one, and of course the snapper circuit, and this is the other sense. So all this goes up to this little controller, and this controller drives the two individual gate drivers. You'll see here they smear this PCB in a thick layer of varnish, so it's not going to cause problems when there's a high humidity. Here we have the gate drivers for the two PFCs. They are blown up, so you can see the crystal inside, and this is why this one is of course broken. This will be the charge diodes. You'll see here we have the NTC and the relay that shorts the NTC. So the 300 volts goes here through these two diodes and charge the main capacitors. When the voltage is high enough on the capacitors here, this voltage goes through a main fuse here. Here is a 10 amp fuse. The master fuse on the input side is 20 amps. So 20 amps times input voltage is quite high. And then the rectified voltage here, and the PFC raises this voltage to 379 volts regulated DC. So this goes through this 10 amp fuse, so that is 3.8 kilowatts of potential power going to the main converter. Also, I've removed the two secondary side transmitters. So that was the first switch mode converter doing the PFC, and then we have the business end converter, where we see two transformators that is going to the output. You can see it here on the assembled one. What you will see here is that the 379 volts goes through the fuse, and then this little baby here is also a switch mode converter. This is a flyback controller, all in one little package, and together with this transformator is a flyback system. So there's actually 4 windings on this, 2 secondary sides that is floating, and then there's also a floating output here for the gate drivers, and of course there's the primary winding, and here is the flyback diode, by the way. So this system starts up when the main voltage is only like 60 volts or something like that, and then it generates all the different voltages that is needed for the entire circuits. What you see is here on the main power supply. At first I thought this could be a full bridge, but this is of course not a full bridge when you look into it a little bit more deeply. This is a 2 FET forward, and this is also a 2 FET forward. So you can actually look at this as one switch mode, and this is another switch mode. But these two are running in interleaved mode. Like the other controller again, they change time when they are running. So in a 2 FET forward, both FETs are on at the same time, and then they turn off. And then these two are on, and then they turn off. So it's interleaved between these two. The two outputs here are connected together. It is with a center point. I don't know if that is easy to see. We have 2 black wires and 2 white wires. So in this case, the 2 white wires, they're connected like this. Maybe I should show this on the other one. See those 2 wires here? That will be the 2 white wires, right? So those goes to a thick metal stick that distribute all this current to 3 field effect transistors. I took out one of them because that was shorted, and the other 3 for the other half. So that means the 2 FET forward, they are running in push-pull mode, and what you have here, that will be the 2 free running diodes. That goes from the coil, or from the ground to the output via the coil. So you charge the coil via the 2 different FET controlled systems, and then you have a free running diode that continues the current to the output. I will explain this again on the schematic that I've made for this, so it should be easier for you to understand all these details. Also, this power supply contains something very interesting. If you look at the positive output after the coil, then there is this module, the output O-ring module. I took this out because the whole system was blown up. So this is the O-ring module. You see 8 field effect transistors in parallel with ultra low on resistance. And there is also a little controller to drive the gates. This controller contains an internal switch mode converter that will generate a higher voltage for the gates. Because of course here you have 48 volts input from the main converter, and you also have 48 volts output, but you need a higher voltage on the gates in relation to its sources, and the sources connected to the plus. So this is done inside this chip, and this is causing a lot of EMC problems, by the way. And here's the little sniffer. Let's looky. So this is from 50 to 500 megahertz. And you see, this is actually the loop, the power supply loop area for this IC. And this is why you're having EMC problems with this Well power supply. because of this IC that drives the gates. Damn it. So yeah, that is basically how it is. You see the output here, got one single capacitor and all the other capacitors here on the output. So 6 of them is connected to the 48 volts before the O-ring module, and the last capacitor is the output after the O-ring module. That is, of course, if that is smart. If this power supply blows up, the O-ring module will disconnect the internal. There will still be a diode from the internal parts to the output, but that will be 0 volts in case everything here is blown up, right? And then anything else from the outside will still be able to deliver 48 volts in, because it will be stopped by the O-ring module. So that way it is smart for safety if you have, again, a parallel system, or you have voltage here like batteries, or this is used as a charger or whatever. Also, I took out the CPU board. You see this is connected to the 2 different connectors. This is the secondary side, or secondary voltage part of it, and this is the primary side before the transformators. So that will be all the main switch mode signals. And of course I did a little bit of research on this module to figure out exactly how it works. And this is the main switch mode controller that is doing the interleaved 2-FET drive for the 2-FET forwards. And this is UCC28220. So you can look this up. I tried to boot this up, however this one is blown up as well, so I'm not able to get output out of this one. But then all these optocouplers, they're not doing the PWM or the regulation or anything. It is just the supervision of anything else. It is done via the optocouplers. And yeah, I tried to disconnect the crystal here so I could see how everything else is operating on this PCB. And here I removed these 2 isolators. They're also working in a very interesting way, because they're working at 2.1 gigahertz. These 2 isolators, and they are called SI8421, and they are 2-way isolators. There's another one on the back side. So I got real curious and looked up the data sheet for the data isolators, the SI8421. There are 2 of them, and they are both 2-way. And I think it was really interesting to see they work from DC to 150 megabits per second. So that is interesting. Very, very low propagation delays. So I was reading a little bit more in the data sheet about how they appear to be working. And they contain of a little oscillator, or they call it a modulator. In the old data sheet that I found, this was actually explained with both this schematic, where they say there is this RF oscillator, and it obviously turns this RF on and off, and then there is some sort of a magnetic coupling between the 2 halves, the transmitter and the receiver. And since this one is a 2-way, there's both a transmitter and a receiver on both of the half sides of this component. So I stripped a few pages more down, and then I saw this 2.1 gigahertz. This is interesting. And they even came up with a table of interesting frequencies and levels. And they also said something about how to measure this. It seems like this is a signal that is in like a different mode from the transmitter side to the receiver side, or the isolated to the non-isolated part of this IC.
I couldn't pick up anything on the board, so I took off the ICs and I powered them up like this with capacitors with really long leads to make it really bad design, and inductors on each side just like this, so I could feed the transmitter and the receiver side with the same power supply. And like you can see, I put my spectrum analyzer on the two grounds on the two different sides. So if there was some sort of a difference inside this chip, I should be able to pick this up on the spectrum analyzer. So I'm zooming in on 2.1 gigahertz center frequency and a 200 megahertz span. I'm enabling amplifiers and removing attenuators and all those fancy things, and enabling the EMI filter. So that means this will be like it will be detected in an EMC lab. So this signal is really, really weak. And as you see, it is plus minus 40 megahertz from the carrier. So it is running in spread spectrum mode. Really smart for making low EMI.
This NPN transistor is the 5 volt regulator together with the, that is all the decoupling and filtering. And there you have the signal diodes and all the components used for the 5 volt regulator. It takes 12 volts input on this pin, and then it makes 12 volt, 5 volt for the CPU. And on these pins here, you have the other isolated input, another 5 volt and another 12 volt that is isolated, like I said. And this is for the user side communication, for paralleling, for arraying communication, and for current sharing communication to other units. And this has to be isolated, of course. So that is great. I could just connect it all together for experiments with this PCB. And this will be opamps for monitoring currents and voltages. And here is the input for the fans. I even made a little schematic for this PCB. Or just a little roadmap for me to figure out what is going on. Where is all the signals? So this will be the switch mode controller. You can power this up and see that it is working at 90 kilohertz. You have the two current sense inputs, and to start this up, you put in 378 volts via 1 mega ohm resistor, and then this one will boot up when the input voltage is correct, within the correct span as well. And then of course the 12 volt comes from the auxiliary supply to drive this chip. There is the RS-485 converter that is used for the communication that is available on this connector. So RS-485. I didn't break down the protocol yet. It is running in a little bit special format. I wasn't able to figure that out yet, but maybe I will be able to do that one day. And the other two parts, that will just be opamps. There's also a really funny, it looks like data, but it is like a pulse width communication format that is on this pin. It is coming every 100 milliseconds. It looks like a little bit of a heartbeat, but it does contain some sort of intelligent life in it as well. It's really a funny signal. So please, if anybody knows what that is doing on this connector, add it to the comments, and I will be happy to know how that works.
Here is my own block diagram. I made it a little bit more detailed to explain how this power supply works. The input filter looks a lot like any other power supply, so we don't go too much in detail with that one. We have the two parallel rectifiers. I only showed one. And this is the NTC and relay for inrush current protection. There's also two other diodes from this point to the capacitors. Those will of course help with the inrush current and to charge those capacitors without overloading these two. Also this high peak current during power on. We don't want to blow up these two inductors. Of course they are really big and should be able to handle it, but somehow they thought it was necessary for two extra diodes to go that way. If we look at the PFC system, it's not shown here on this schematic, but there are two current sense transformators on these two drain points. On this scope picture, I put in an extra wire into the two transformators so I could see how they are working in interleaved mode. And of course this PFC is measuring the input voltage, and it is following the sine wave, and one of them actually starts and stops a little bit before the other one, so it goes in single PFC mode. And this is because it wants to achieve a much higher efficiency. When you don't need both of them, you only need one of them. And if you only use one of them, you have half the switching losses. So this is really a nice way to up the efficiency. Then there is an auxiliary supply that is also running off the 378 volts. It is using the top 256 converter. Please look up the data sheet. It is a really smart and efficient converter as well, and it runs over a very wide input voltage range. So this way it will be able to empty the capacitors. See, let's look at the business end of this converter. It's really an interesting topology. I haven't seen this before, and I've been googling the internet for a long time, and I was not able to find a block schematic of anything made exactly like this. So a 2-FET forward isn't really something unique. This is a very normal way to convert high voltage at high efficiency. The smart thing is that you only have your rail voltage over your fets, so you don't need to have very high voltage fets. Of course you have almost 400 volts, so they picked 600 volts fets just to have a good safe margin. But normally you would use more than double and then add a margin. So you will normally have 600 or 1000 volts fets if you didn't use the 2-FET forward topology. So this is a really good way to up the efficiency as well. Of course these two are switching at the same time. This is shown by the paralleled input of the gate drivers. And then we have the PWM controller. It is also measuring the current on each of the ground side FETs. And I tried to measure the voltages on this point and on this point on this scope picture to show you that they are the two 2-FET forwards. They are working in push-pull or in interleaved mode. But when you look at it on the secondary side, you would of course call this a normal push-pull. Each of the synchronous rectifiers are driven by an extra winding on the transformators. There are also other windings on these transformators here made to drive each gate driver circuit. And when none of the outputs are driven by FETs, the diodes here will lead the power to the output. And I already explained about the O-ring hot swap module, and it is here you can see the higher gate voltage is needed. You can also see the body diode in all the FETs, and this reveals of course that this is used for protection against something coming from outside in the case it is blown off, or it is used for current sharing because there's a really fancy thing about the TPS2412. It is able to generate a linear variable gate voltage, so that is actually adding a little bit more on resistance or a little bit more voltage drop over this over the fets. It is only a few millivolts, so it isn't really heating them up a lot, but this is for a current sharing of more units. It's a pretty smart way to do it. I also went to different EMC labs to perform tests on this power supply, together with a few meters of cable on the input side, and on the output side I got 5 meters of cable and a load. I'm only loading it about 50% in different EMC labs, like you see here. And of course the result is very devastating. The output radiated noise is 40 dB over limits, so that is a big problem. So I created my own filter. This is a very effective filter for the input and the output. And I wanted to see if I could get a little bit more attenuation by adding ferrite clamp-ons. And with all these things together, I was able to get it all the way down to almost acceptable level. I tried with horizontal and vertical antennas and with different filters, and this is my before and after experiments.